So we're going to be looking at the identification of unknowns. This sort of comes at the end of all of the redox chemistry, the trends in group 2, trends in group 7, and we would have covered some of those tests individually, but now we're just going to bring them all together. So we're going to quickly recap the 4 different gas tests that you need to know from GCSE because they're still useful and relevant, and then we're going to talk about the different tests we need to know for unknown ions. The first test we're going to talk about is the hydrogen gas test. Now, you have to make sure that you are saying the method and the result. Just saying squeaky pop test is not good enough. So, hydrogen gas test, you add a lit splint and it burns with a squeaky pop. And the reason for that is because it is a little combustion reaction, almost like a tiny explosion in that test tube, which is what gives you that little pop sound. Oxygen gas test, add a glowing splint and the splint reignites. Because if you increase the oxygen, then the combustion is able to take place more readily. So a glowing splint doesn't have enough oxygen in the atmospheric composition to combust, but if you put it into a test tube or a container that contains more oxygen because you've collected it, then it will be able to combust, so it will reignite. The carbon dioxide test, you bubble it through lime water and it turns cloudy. And the reason for this is that lime water is calcium hydroxide, aqueous calcium hydroxide, and when you bubble carbon dioxide through it, it forms insoluble calcium carbonate. So you're actually forming a precipitate of insoluble calcium carbonate, which is what makes it go cloudy. And if you were to leave it, what you would see is that calcium carbonate would settle on the bottom. And then finally we have the chlorine gas test. You need damp litmus paper, which will turn red initially and then bleach white. And this is one of the reactions that we looked at when we were looking at group 7. So chlorine reacts with the water, which is why the litmus paper must be damp, and it produces hydrogen chloride, which is acidic, which is why it turns red, and hydrogen chlorate, which is the bleaching ion. The chlorate ion, the ClO, is what is responsible for bleaching it white. Now you should remember that this is an example of a disproportionation reaction because the chlorine is being both oxidized and reduced. The oxidation state of the chlorine, the elemental chlorine, is 0, and the chloride in the hydrogen chloride is -1. So it's being reduced from 0 to -1, but in the hydrogen chlorate, the chlorine in that molecule is +1. So it has been oxidized from 0 to +1. So it's a disproportionation reaction. So the metal cation test, now these are the ones from the GCSE, and they are still relevant. They're not relevant right now, but it didn't seem to be worth removing them because when you do the inorganic transition metal complexes, you will need to know these colors of precipitates and a great many more. But actually a good starting point for the transitional metal inorganic chemistry is to know the colors of the hydroxide complexes from the GCSE. So the first thing you'll notice is that aluminium, calcium and magnesium all give you white precipitates, and the observant amongst you will realize that actually that's because neither of those 3 are in the transition block, whereas copper, iron and iron 2+ and iron 3+, they're transition elements. That's why they form colored compounds. That is one of the defining properties of transition elements. They form colored compounds. So aluminium, calcium, magnesium, not transition metals, so they are going to form white precipitates. The aluminium will redissolve if you add excess sodium hydroxide, but the calcium and magnesium will not. So the copper 2+ forms a blue precipitate when you add sodium hydroxide. The iron 2+ forms a green precipitate when you add sodium hydroxide, and the iron 3+ will form an orangey brown precipitate, sort of rusty coloured precipitate when you add sodium hydroxide. And these are the ionic equations for the formations of those precipitates. So we have aqueous solutions, so we've got the aqueous metal solutions, and we have the aqueous hydroxide ions, which obviously come from the sodium hydroxide, and we're forming these insoluble precipitates. Now the halide anion test, now this is largely the same as it was at GCSE. You add acidified silver nitrate, and because it's silver nitrate, the acid we acidify it with is nitric acid, because then we're not introducing additional ions to the solution. There's already nitrate ions from the silver nitrate. There's already H plus ions from the water because it's in solution. So by adding silver nitrate, we're not introducing any additional ions. And if your compound contains a fluoride, it will form silver fluoride, which is a soluble, so it will form a colourless solution. However, if it contains a chloride, it will form silver chloride, which is an insoluble white precipitate. If it contains a bromide, it will form silver bromide, which is an insoluble cream precipitate. And if it contains an iodide, it will form silver iodide, which is an insoluble yellow precipitate. So these are the reactions. Again, ionic equations showing the aqueous halide ions reacting with the aqueous silver ions to form the silver halides. And with the exception of silver fluoride, they are all insoluble precipitates with different colours. Now, in reality, you probably aren't going to be testing a chloride, a bromide, and an iodide side by side. So it's sometimes quite difficult to determine whether is it a white precipitate, is it cream? It's maybe not so clear just to the naked eye. So we can use their solubilities in ammonia to distinguish between these three precipitates. So the first thing you should do is add dilute ammonia. Silver chloride will dissolve to form a colourless solution. However, the silver bromide and the silver iodide will do nothing. They won't react, they won't dissolve, the precipitate will stay as it was. So if you add dilute ammonia and it dissolves, then you know you've got a silver chloride. If nothing happens, you then add concentrated ammonia, and the bromide this time would dissolve to give you a colourless solution, but the iodide won't. So if you add dilute ammonia and it dissolves, then it's silver chloride, and if it doesn't, you move on to adding concentrated ammonia, and if it dissolves, it's silver bromide, and if it still does nothing, then you've got silver iodide. Another test for the halides, if you've got sodium halides, is to react them with concentrated sulfuric acid and record the observations. So as you go down the halides, as you go down group 7, the halides, their reduction potential increases. So they are able to reduce, so iodide is able to reduce the sulfur in sulfuric acid further than chloride or fluoride. So you get different products of the reaction, and you can use the observations of these reactions to identify them. So in a nutshell, the observations you're looking for, if you get misty fumes being produced and nothing else, then you've got a sodium fluoride or a sodium chloride. If you get a pale brown gas being produced, then you've got a sodium bromide. And if you get a really sort of bad rotten egg smell, then you've got sodium iodide. So the reactions that occur are these. So this is for the fluoride. So the sodium fluoride reacts with the sulfuric acid to form sodium hydrogen sulfate and hydrogen fluoride. And it's that hydrogen fluoride which gives you the misty fumes. When you've got sodium chloride, you get a very, very similar reaction, only instead of getting hydrogen fluoride, you get hydrogen chloride, but you still get the sodium hydrogen sulfate. And again, it's the hydrogen chloride which causes those misty fumes. So the chloride and the fluoride react in the exact same way. The bromide, however, is a stronger reducing agent and is able to reduce the sulfuric acid to SO2, sulfur dioxide. And it does that by doing the exact same reaction to begin with. It produces sodium hydrogen sulfate and hydrogen bromide. But that hydrogen bromide then goes on to further react with the sulfuric acid to form elemental bromine, sulfur dioxide gas, and water. And it's this bromine that's being produced that is, you would observe it as a pale brown gas in the reaction. The iodide, which is the got an even stronger reducing potential than the bromide. Again, follows the first two steps, the same as bromide did. Reacts with the sulfuric to form sodium hydrogen sulfate and hydrogen iodide. That hydrogen iodide can then react further with the sulfuric acid to form elemental iodine, sulfur dioxide gas and water. But then the hydrogen iodide also reacts with the sulfur dioxide to produce elemental iodine, hydrogen sulfide and water, and it's that hydrogen sulfide which gives you that really bad rotten egg smell. So you can use the observations of these reactions to identify whether you have a sodium fluoride, chloride, bromide or iodide, and you need to be familiar with these observations and you need to be familiar with these reactions. We've also got the sulfate anion test, which is simply add acidified barium chloride, and because it's barium chloride we use hydrochloric acid to acidify it. You could also use barium nitrate, in which case you would use nitric acid to acidify it, and then record the precipitate formed, and you would get a white precipitate in the presence of a sulfate ion, and that precipitate will be barium sulfate. So here we have the ionic equation. We have the aqueous sulfate ion reacting with the aqueous barium ion to form insoluble solid barium sulfate, which presents itself as a white precipitate. And finally, we have the carbonate test. Add an acid, any acid, and it will react with that carbonate to produce carbon dioxide. And you can prove that it's carbon dioxide by bubbling it through lime water and recording if it goes cloudy. So the reactions here, we've got the carbonate ion reacting with the H+ from the acid, producing water and carbon dioxide, and then we can identify that carbon dioxide by bubbling it through lime water, which is calcium hydroxide, to form that insoluble calcium carbonate, which is why the lime water turns cloudy. Now the last thing to note from this is, if you remember back from when we were talking about the group 2 carbonates, pretty much all carbonates, with the exception of group 1 carbonates, are insoluble solids. So if you were testing unknowns and you had a carbonate unknown, so let's say for example sodium carbonate, but you didn't know it was sodium carbonate, and you went and added silver nitrate because you were trying to see if it contained a halide, you would form silver carbonate. Now, silver is definitely not a group 1 element, so silver carbonate would be an insoluble solid. So you would get a precipitate formed, which if you didn't know what your solution was and you added silver nitrate and then you got a white precipitate, you would logically conclude that you must have a chloride ion. But actually what has happened is it's silver carbonate and you've given yourself a false positive. If we took that same unknown, that sodium carbonate, and let's assume we didn't know it was sodium carbonate, and we thought, well, maybe it's a sulfate, and we added barium chloride to it, it would form barium carbonate. Barium is not a group 1 element either, so barium carbonate would be an insoluble precipitate. And again, we would think perhaps that we had a sulfate ion because a precipitate was formed, but actually again it's a false positive. Now there's nothing you can do to prevent the false positive other than, if you've got some unknowns, do the carbonate test first. The only anion that will produce a gas which turns lime water cloudy is a carbonate ion. So if you've got unknowns, the first test you should do for the anions is add an acid. And as soon as you add an acid, if it bubbles and that gas produced turns lime water cloudy, then you know it's a carbonate, and then you can exclude it from all of the other anion tests. Then you could go on to do your halide tests and your sulfate tests without having to worry about false positives from any insoluble carbonates that might be formed. So just to recap, you need to make sure that you know the halide tests with silver nitrate and the colors of their precipitates. Make sure you know the equations as well, the ionic equations for all of these tests. Make sure you know the solubility of those silver halides in ammonia, both dilute and concentrated, the observations and equations for the reactions of sodium halides with sulfuric acid. Again, make sure you know the observations, make sure you know the equations. And then the same, you've got the anion test for carbonates and sulfates. Make sure you know the reagents, make sure you know the observations, make sure you know the methods. And again, all of the ionic equations you need to make sure that you know. Other than that, the other thing they might ask you to do is to identify group 2 elements based on their solubility. And again, that is just a case of if you were given some group 2 oxides or some group 2 hydroxides or perhaps some group 2 sulfates, you should remember their trends in solubility. And then what you would do is you would add water to them, I don't know, 5 centimeters cubed at a time until they dissolve, and then you should be able to put them into order of solubility. And if you remember that group 2 oxides get more soluble as you go down the group 2 hydroxides get more soluble as you go down the group, but group 2 sulfates get less soluble as you go down the group. So if you had a selection of group 2 compounds, you should be able to, by testing their solubility, at least order them. You might not necessarily be able to identify them, but you can certainly put them into order. So perhaps you had 3 unknowns and you knew that one of them was magnesium, one of them was calcium, one of them was strontium, but you didn't know which. You would be able to use their solubility to put them in order of solubility, and then you would be able to identify which was which. All of this ties into the required practical for identifying unknowns, which we will do at a later date.